Okay, so it's 5-1 and I will start. I hope I'm audible to you, Venkat Krishna. So in this week lectures, you have learned about forward kinematics and the DH algorithm. Basically, you have learned how to get the transformation matrix from that from frame I to I plus 1 or equivalent way of writing from frame I minus 1 to I. Okay, so I will just derive it again. Um,
Yes, sir.
yeah, so I will just derive it again now and to just make it clear with the Craig convention and explaining to you with the help of screw displacements that how it comes. Okay, so if you were there in the last session that I took, you might know this diagram already, but I will go over it again. So here I have drawn three links. Okay, these links look like this because I have drawn them to be very general links. They can have bends in between. Uh, they can be twisted with respect to each other. Okay, but they are rigid. Okay, the only assumption that we took that these links are rigid. Okay, and we said that link I minus 1 and link I have a common axis of rotation that we call ZI. Okay, so basically we say that the joint that is between link I minus 1 and I is what we call I. Okay, it is our convention. This is what we have chosen to call it. Using this convention, the joint that is between link I and I plus 1 is what we call joint I plus 1. Okay, so no issues there. And then we assigned Zi to this axis of rotation. Okay, this axis of the joint for both joint I and joint I plus 1. And then what we did was we assigned this xi to the common perpendicular to zi and zi plus 1. Okay, I'm just going over how I fixed these frames in the last lecture for people who were not there. Okay, so using and I, I I think I'll wait for more people to come. Yeah. Okay. Okay. So and then what we did was this distance, this shortest distance between Zi and Zi plus 1, we called that AI. Okay, so basically the link length. Okay, you can also call it Li. It doesn't matter that much. Okay, so what is AI, Li formally? Okay, so if I want to write it, AI is the distance between Z, the unit vectors Zi plus 1 and Zi as seen from or you can write along xi axis. Okay, so this is what our AI is. Okay, and similarly we had defined alpha I, that was the angle between zi plus 1 and zi along the same xi. Okay, and the rest of the two parameters were d I plus 1 and theta I plus 1. Okay, so what were these? This were distance between xi plus 1 and xi along zi. Okay, and then this was angle between xi plus 1 and xi. Think, yeah, this is along zi plus 1. Uh, and keep it between people as they come. Hmm. So, any problems in this? Anyone? No?
No problem, sir.
Okay. So, now using this, okay, I'll try to mark these in this diagram, okay? Okay, so this is our zi. So, this angle now, okay, along xi, okay, this becomes your alpha I, okay, and then this distance over here, I'll mark it in black. This distance, this becomes your di plus 1. Then if I, since I had made xi, I just shifted xi, okay, just because these xi zi are vectors, so I know that I can just, I shifted them to make it easier for us to measure distance or any parameters between them. So this is what I'm calling theta I plus 1. And so what else is remaining? Nothing, right? Okay. So now all of you can see this figure. How do we, if we want to go from frame I, okay? So at joint I, we have assigned frame I. And at joint I plus 1, we have assigned frame I plus 1. So from frame I, what are the transformations that I should do so that the frame ith frame coincides with I plus 1th frame? Do you get it? Yes. Okay, so first transformation that we can see is that this origin of this frame I, let me call it A, and let me call this point that it coincides with as point B. Okay, and the origin of this frame I plus 1 is C. Okay, so the first transformation is displacement along xi, right? I take this point A and then I shift it along xi until it reaches point B. Okay, so the first transformation is, you know, uh, okay, so the first transformation is displacement along xi, okay, or displacement along an axis. So do you know how do we represent displacement along an axis? Like what is the mathematical transformation matrix that we use? Okay, so I'll do one thing. I will define two transformations. Okay, TR. Okay, I'll bring it from here. Like any general transformation matrix, you know, is of this form. Okay, so I'll just break it into two parts. I will say that there is one TR. This TR contains, it contains only information about the rotation. Okay, and this T tra translation, it contains information only about the translation. Is that fine? Okay, So I can see that the first transformation that I'm doing is a translation transformation, and the distance is AI. Okay. And then along this, now at the new position, along the same xi, okay, I am rotating everything by alpha I, okay, because I need to rotate along xi to get from zi to zi plus 1. Okay, so that second transformation, okay, so this transformation followed by a rotation transformation. mm, I should also specify which axis I'm using. Okay, so AI along xi, and then after this I do biangle alpha I about the same xi. Okay, so now at this point you can see that we have rotated this zi by alpha I. So our xi is here, that I marked in black over green. Okay, but our new zi after this transformation is coincided with zi plus 1. Okay, so now zi and zi plus 1 are on each other. Okay, they are coincident, and that is what we wanted partially. Okay, but our job is not complete yet. We wanted both of the frames to be, you know, over each other, like overlapping each other completely. And I just made a mistake here. We have only translated to point B. Okay, so right now xi is here. Okay, that I think I should mark in some other color now. I'll use blue. Okay, so r- right now xi is at this point, at point B. Okay, so now what we need to do is, now I think you guys can also see along this z, okay, either zi or zi plus 1, I can say anyone because now both are coincident. Okay, I need to displace, okay, I need to translate by di plus 1, right? And then after I have translated, my z will be the same, but my x would have now coincided with, I mean, my origins would have coincided. Okay, now since my origins have coincided, the final thing that I need to make sure coincides is xi plus 1 and xi. Okay, and what is the, final transformation that I need for that? Can anybody say? This is, I will write di plus 1 along what? Zi. Yes, anyone? What is the final transformation that I need to do to make them coincident, both the frames? Okay, I'll I'll just write it.
Excuse me, sir.
Yes, yes, Venkat.
Yes, sir. So, can we displace the object on ZI axis, like towards the LI distance?
Object on the ZI axis. I
Yes, sir.
don't follow you. Like, what exactly is the question? There is a point on ZI axis?
Not really the point. I'm like talking about the specific object.
The link. Like, what is the object that you're
Yes, sir.
talking about here? Because what right now we are doing here is we are
Hmm.
displacing the, or translating the frames itself. Okay, so this frame I, okay, that is a combination of, if I,
Yeah. So I was talking about the frame.
yeah, yeah. So see, what the transformation do is we apply transformations on frames. Okay, so when I say, because these frames are also made up of vectors. Okay, so I can apply transformations on these vectors such that they can rotate or they can
Hmm.
translate to any other point, right? Uh,
Yes, sir.
to motivate what I'm saying further, let us say there is a fixed frame. Okay, let us call these axes as E1, E2, and E3. Okay, and let us say that there is a point denoted by P. Okay, and the origin of this frame is marked as O. And now at this point P, I attach an arbitrary frame. Okay, that is, let's say, E1 prime, E2 prime, and E3 prime. Okay, now if I say that I am transforming vector OP, okay, like I'm multiplying it with some transformation matrix, wherever P reaches again, this frame will also go along with point P, right? And let us say you have attached this frame in such a way that E1 is aligned with this vector. Okay, so the frame will also get rotated, okay, in an equivalent way. Is that fine? Venkat, did I clear you down
Yes, sir.
or did I confuse you further? Okay,
Sir, so
yeah, yes,
you are trying to say that if we move a point, then the frame will also move with it, right?
yes. We are moving the origin of that point, okay, and the orientation, okay, because a point does not have a concept of orientation, right? That is why we attach these three axes there. We attach a frame there, okay, to represent the orientation. Okay, that is what we are doing here. Okay, so we are saying that we want the final transformations that can
Yes, sir.
convert. Okay, shit, no, not yeah, that can convert this frame I. Okay, this frame I to frame I plus one. Okay, and why we want that transformation? Because we know that now we can use that transformation to convert the points in respective frames into each other. Okay, I will come on that further. Okay, so basically, first of all, what you keep in mind is you want a final transformation that you know that can take frame I to frame I plus one. Okay, and this final thing that we need to do here is we need to rotate by theta I plus one along z axis. Okay, and keep in mind that every successive transformation that I'm doing is you know along the new axis, okay, after each transformation, not along the old axis. Okay, so keeping that in mind, um, let us you know focus on this one first. Okay, so this is a displacement or translation along xi followed by a rotation. Okay, rotation along the same axis. Okay, so do you know what these are called? Okay, the transformations in which you translate and rotate along the same axis. Okay, so there is any given arbitrary axis. Okay, you are translating and you're rotating along the same axis. Okay, so have you seen any motion of this kind happening anywhere? Okay, where when you translate about or vice like conversely when you rotate about a particular axis, you also translate about that axis. Hmm. Okay. Um, does the word screw ring any bell? Yes, anyone? Okay, so you we all know that what happens in screw is when we rotate them in their particular fixture, they translate automatically along the same axis that we are rotating them in. Okay, so this name screw displacement is motivated by that motion. Okay, so when you translate about a particular axis and you rotate about the same axis, okay, so then this combined motion, okay, it does not matter which one do you first, you do first, okay. You can also rotate first and then translate. Okay, what matters is the final transformation. If you have translated and rotated along the same axis, okay, then that displacement is called screw displacement. Is that fine? Okay. Now, as I had
Yes, sir.
made two different transformation here, one for single rotation and one for separately transformation. Okay, I will, you know, define a screw displacement transformation. Okay, that takes, let's just not write di. Okay, let us write some translation. Okay, and some rotation about a particular axis. Okay, so now this screw displacement is written as, rotation about, I should not write x. Okay, about ei. Okay, so rotation about this particular axis by this angle and this. Okay, so now you might be thinking that what is the difference between this screw displacement and the previous general displacement that we have written here. Okay, so the difference is just that the form of a screw displacement is easier. Okay, you can say that it is an intermediate step to get from these two separate, so to get from fundamental matrices to homogeneous matrices. Okay, it is an intermediate step. Okay, so for our given, transformations, we can write that it was a screw displacement di alpha I along xi. Okay, so since it is along xi, we know that the rotation part will be like this. Okay, okay, where c alpha and s alpha are just replacements for cos alpha and sin alpha respectively. Okay, and then along the same xi, I went di, okay, and then the homogeneous part. So this is the first screw displacement. Okay, and what was it followed by? Let us say that I call it screw displacement 1. Okay, so the second screw displacement, because I'm calling it screw because I already know that it was a screw displacement, but you have to make sure of it. Okay, so it is a translation and rotation about zi axis. Okay, both of these, okay, along the new zi axis, if I should add. Okay, so this is, oh wait, this is not di. You guys can, you guys should spot these kind of mistakes and tell me. Okay, so now the second screw displacement was about the existing zi. Okay, there is another way to write it. Okay, but I will discuss it after. Okay, like along the actual zi plus 1. Okay, but for now I will not discuss it. Okay, I will tell you what is the, I will tell you for, like in after I've derived the transformation matrix, that what is actually the difference in using this zi and zi plus 1. Okay, you can also make it out that if I use zi plus 1, then I should, basically the difference comes if you have to pre-multiply or you have to post-multiply this second transformation with the first one. Okay, so since it is along z, okay, so this becomes cos theta I plus 1 minus sin theta, and then cos theta I plus 1 along z we have d I plus 1. Okay, and since now I had rotated along the existing, or the not existing, along the new axis, okay, along the transformed axis, okay, so the final transformation, okay, from frame I to I plus 1 should be given by the first screw displacement, you know, post multi no yeah post multiplied by the second screw displacement. Is there any problem in this, like why post multiply?
Sir, can you please once explain why it is post multiplied?
Yes. So why it is post multiply? In the lectures, you might have, as sir might have explained, that when you are transforming, okay, let I will, take an example of rotations. Okay, let us say this is E1, this is E2, this is E3. Okay, the one kind of rotation that you have studied is yaw pitch roll rotation, right? The rotation representation. Okay, it is also called ZYX rotation. Okay, now there are two kind of ZYX rotation. One is fixed axis and one is what we call the Euler rotation representation. Okay, the difference in that is if you use the Euler rotation, okay, so if you use Euler ZYX, then that says that you first rotate about Z, okay, rotate about Z axis or the E3 axis in our case. Okay, in our case, X is equivalent to E1, Y is equivalent to E2, and Z is equivalent to E3. Okay, so what Euler says is that you first rotate about Z by, let us say, phi. Okay, then about the new uh, axis, okay, new Y axis. Okay, so let us say that it is E2 prime. Okay, I've rotated about E3. Okay, so these guys go from here to here, and this rotated frame is now even prime, E2 prime, and E3 prime and E3 are the common. Okay, so I can just write this. So about this new axis, I should be consistent with what I use. Okay, about this primed axis, I rotate by theta, and then about the further new axis, okay, the latest x-axis, uh, I rotate, about the final angle. Let us say psi. Okay, so the final rotation matrix that I have to write, okay, will look something like this. Okay, in terms of fundamental rotation matrices, so it will be rz phi multiplied by ry theta multiplied by rx psi. Okay, but if you had used fixed angle zyx, okay, this is Euler zyx. So in this, what we do is we first rotate along z, okay, and then we rotate along the previous y-axis, okay, the original y-axis, and not the new y-axis. Okay, so you rotate along the original y-axis by angle theta, and then the third rotation is also along the original. Okay, these are the original ones that do not rotate, that I mean that we had rotated, but these were the initial ones. Okay, and let us say psi. So if in this case, when you want to write the rotation matrix, okay, so you write in this form. Okay, you pre-multiply all the transformations or all the rotations. Okay, so this is the difference, or these are the conditions where you post multiply or pre multiply. Is that fine now?
Yes, sir. Understood.
Okay, so now this is the reason, okay, why I have post multiplied the second transformation here. Okay, if I had used this one, okay, this along zi plus 1, if I had used this, then I would have written using pre multiplication. Okay, like let us say that this is a primed second. Okay, but since I have not done that, I'm not using it. Okay, so now to get the final transformation. Okay, transformation, because this transformation now we know, because we have interpreted geometrically that these, all both of these screw displacements take us from frame I to frame I plus 1. Okay, so we know that multiplying both of these, this transformation gives us from I to I plus 1. Okay, because the this is what makes the frames coincide. If you have doubt at any place, you can just stop and ask. Okay, like stop me and ask. Okay, so what we will now do is we will just see that what is the final transformation matrix. Okay, and in this case it was c theta I plus 1. This is theta 0 0 1 I plus 1, not 0 I plus 1. Okay, so if we multiply both of these, okay, what will be there at the first element of the first row or the first column? Let us fill column wise. Okay, so can anybody tell what will be the first element of the
Cos
first row?
theta I plus 1.
Yep. Okay, what will be the second element of this column? The first column? Hmm.
Minus sine theta I.
Okay, minus sine theta I.
Oh, sorry. You're asking about the second row first
Yeah, yeah.
column.
So
Okay.
second element of the first column.
Second element of the first column. It should be cos alpha I sine theta I plus
Sine
1.
theta I plus 1. Okay.
Sine theta I plus 1. And
The third one.
that's it.
Okay, and the
The
third element,
third element is
similarly like
sine
this.
alpha I cos, sorry, sine alpha I and sine theta I plus 1.
Right. And the last one will be 0,
0, yeah.
right?
All
Sim
last row will be the same. 3 zeros and 1.
okay. So three zeros and a 1. Okay, now let us fill up the second column. Okay. So what will
Okay.
be the second column?
So the second column, it should be minus sine theta I plus 1.
Hmm.
For the second row, second column, it should be cos alpha I and cos theta I.
Yes. I plus 1.
Yeah,
Theta I plus 1.
yeah, I plus 1. Yeah.
Yes.
And then sine alpha I
Hmm.
multiplied with 0. Okay, cos alpha I
Cos
for
theta
the
I plus
third.
1.
Yeah, cos theta I plus
right?
1.
Okay. And the last and the third column, okay, since it, the third column in the second matrix has a 1 there, okay, so we
Yes.
just replace it with the third column in the first matrix, okay, because
Okay.
um
Yeah, it is going
okay,
to
because
multiply.
this is what, because the rest of the elements are 0, so this column will be the same, okay. And what will
Okay.
be the final column?
Final column will be AI
Hmm.
0.
0.
No, it is minus sine alpha I into d I plus 1.
Yes, and we can write it like this.
Yes. And di plus 1 cos alpha I.
Okay, so this is your transformation from frame I to I plus 1. Okay, and you can also compare it with the result given in books, because in books it is generally given in this form.
Isn't it
Okay.
cos alpha I? I have written sine alpha I.
Oh, thanks. Hmm. Cos alpha I. Is that correct now?
Yes, I think so. Yes. Similarly, for the third row, second column, I'm not sure whether it is.
No, I think that is correct.
Yeah. Okay.
Third row, second column. Hmm. Yeah, it seems to be correct. Okay. So
Okay.
now to just convert from this to this, okay, you all know what you need to do. Okay. You replace I with I plus I minus 1. Okay. So I'm not going to write what it is, but you can, write it for yourself and verify, is it, similar to the result given in books or not. Okay. So why I derived it for you guys is to show you that you do not always need to remember this. Okay. You need to remember it if you are going for an exam. Okay, because that, deriving it takes a bit of your time. Okay. But if you are just doing research, or let's say you're doing any project or for any homework, and you do not remember this matrix, okay, so one solution is to just look into the books. Okay. And other solution is to go through first principles. Okay. You understand that what, what does it take to go from frame I to frame I plus 1. Okay, what are the basic transformations that you will need? Okay, what are the basic transformations that you are going to need to go from frame I to I plus 1? And then you just multiply those. Okay, so now is there any doubt, is what I would like to know first. Yes. No.
Can you just repeat why we are using pre multiplication and post multiplication? Just
Yeah.
in a
Okay,
short.
we are using post multiplication in this case because the second transformation we have done along the new axis, okay, the modified zi axis. Okay, we that transformation is no longer along this previous original zi axis. Okay, I had moved this axis by ai, and then I had rotated this axis by alpha I. Okay, and now this at this new position I am doing this translation and rotation. Okay, so
Okay.
since it is along the new axis every time, that is why there is post multiplication. If it was along
Okay.
the original axis, then it would have been pre multiplication.
So if we can directly derive like transformation from I minus 1 to I.
Yes,
During that time, we need to do it in post multiplication or pre multiplication.
yes. Okay, so right now you can see that I am going one step at a time. Okay, and for each transformation, I'm using the last transformation. Okay, the new position of the frame after the last transformation.
Okay.
Okay, so when you do that, you do post multiplication. Okay,
Okay.
and the reason for that comes from tensor calculus. Okay, not even calculus, tensor algebra.
Okay.
Okay, like if you want to know about it, you can write an email to me and I will explain to you separately because that is not relevant to what you are studying right now.
Okay. Okay.
Okay,
Right.
so since it is done, we will take a small example. Okay, and that small example is just a 2R manipulator. Okay, let us say that this is O, this is A, and the end effector is at point B, and the length of link 1 is L1, the length of link 2 is L2. Okay, so now
Okay.
I want to know the position of end effector. Okay, now what we are going to do now is to give you an example of what forward kinematics is. Okay, so this is a 2D problem. Okay, but you can we are taking 2D because the calculations are easier, but the concept is the same for 3D. Okay, just the matrices are smaller in 2D. Okay, so the
Okay.
first step for any problem is you assign frames. Okay, because using frames only you can assign these matrices or basically the parameters. Okay, so the first frame that we always assign is the ground frame. Okay, and right now I will use x and y since it is a 2D
So
problem. Okay,
X
so
and Y.
I say that x0 y0 these are the basis vectors of the ground frame. Okay, and
Okay.
z is outside this outside the plane of the paper, so that's why I've
Okay.
drawn it. Okay, so now according to DH convention, where should I draw the frame 1? At point O, at point A, or at point B? Where should I keep the origin of frame
Point
1?
O.
Huh?
Point O,
Yes, exactly. At
because we
point,
have a joint there.
yes. Okay. And because you can also see that this is the axis of rotation for the first joint.
Yes.
Okay. And this Z0, Z1 it is supposed to be out of plane, but I've drawn it just for convenience.
Yeah.
So now, similar to this, where would be my joint? Where would be my Z2 axis or frame 2?
A at point A.
At point A, of course. Okay, so here I'm not, I'll just write Z2. Okay, and I will
Okay.
try to mark it as out of plane. So
Okay.
now where will be the x-axis of frame 1?
Frame one, it is aligned with the origin. That is the base frame.
It is aligned with the base frame. Are you sure? What is the definition, or like how do we know from this that where do we keep xi?
X, uh, along the link axis,
Okay, along the
link
common
length
link.
axis.
Yes, along the common normal, the shortest perpendicular to both zi and zi plus 1,
Okay.
right? So in this
Okay.
case, x1 is along the common normal for Z1 and Z2. Okay.
Yes.
And
Okay. Okay.
what is the common normal for Z1 and Z2? It
The
is
common
along the
normal is
link itself, right?
yes.
Okay,
Yes.
because Z1 is also out of the plane, Z2 is also out of the plane.
Okay.
So this is our x1 axis.
Okay.
Okay. And how do we get y1 now? Because
Should
I have
be.
not discussed earlier here, right? I've only taken z and x. Why I have not written y?
I'm not
Okay, that
sure.
is because I am assuming that we are working with right-handed coordinate frames, and you can all given two vectors in right-handed coordinate frame, two perpendicular or orthogonal vectors, you can always get the third orthogonal vector by just taking a cross product of both, right?
Okay.
So where in which direction is y? It is in the direction of z cross x. Okay, so
Okay.
y1 is along this direction.
Okay.
Okay, and it is perpendicular to x1.
Yes.
Okay, and y0 is along. Similarly, let us say I attach, a frame here at the end effector. Okay, and I call it x3, y3. Okay, and this x3 is along this link. Okay, it is along this link x3.
Okay.
Okay, so z3 will naturally be out of the plane.
Yes.
Okay, so now where will be my x2? Okay, the x-axis of frame 2. Hmm.
X3 and Z3 we have this direction.
Okay, so x2 will be along the common perpendicular of z2 and z3,
Z3. Yes. Z2
right?
and Z3. Yes.
So it will be
So
along
it should be
this link
on the
only.
link to.
Okay,
Yes.
x2. And
Okay.
from z2 and x2, I know where is my y2.
Yes.
Okay, so now we have assigned the frames for the h parameter.
Okay.
Okay, the next step is to make what is called the dh table. Okay, why we make a table and why not just write directly the transformation? Because it just makes our life a bit easier.
Theta.
Okay, so here we will write I, and uh, what were our parameters again? AI,
Yeah.
alpha I,
Alpha.
theta I plus
Theta.
1 and di plus 1.
D plus 1.
Okay,
Okay.
so let us say I'm writing for link 1 first. Okay, now let us say that there is a link 0 that I called ground link. Okay,
Okay.
and then there is link 1. Okay, that I have mentioned with that has length L1, and then there is link
Yeah.
2, right? That has length L2.
Okay.
Okay, so for link 0, okay, what will be the value of AI, alpha I, theta I plus 1 and di plus 1?
0.
Okay, 0.
Alpha is also 0.
Okay, and theta I plus 1?
That is also 0.
Sure. What
I
is theta I plus 1? Okay, so since
Okay,
I
theta
is
I
0,
plus 1. Theta I plus 1, it should be theta 1.
okay, theta 1, because we are defining that the angle between x0 and x1 is theta 1,
Theta 1.
and the angle between x1, the extended x1 and x2 is theta 2. Okay, so then it
Okay,
is theta 1,
theta 1.
right? And
Yes.
then what is di plus 1?
Di plus 1 is L1.
L1. What is D?
D is the displacement.
Yeah, D is the distance between x I. Di plus 1 is the distance between xi plus 1 and xi along zi plus 1. Okay.
Okay,
So
so
is there
it
any
must be,
distance between x1 and x0?
no, there is no distance.
Okay. So this is
So it
0.
should be
Okay. You can also remember it by this, that this di is called the link offset.
okay.
Okay. And this alpha I here is called the link twist. Okay.
Twist.
So link twist, basically, if the z axis of both, the joints of the respective joints at one link, if they are not aligned in the same direction, okay, if they have a twist in them, so that is, you know that is a very crude way of saying that, that is what twist
Okay.
is.
Okay.
Okay. And now we come for link 1. Okay. So, like, what are the parameters for link 1?
It should be AI.
What will be AI in this case?
AI will be
Distance between z,
means
yes,
two Z
z2
axis.
and z1 as given along x1.
Zero.
No, distance between z2 and z1 as given
Okay,
along
L1.
x1.
L1.
So this will be L1. And what will be alpha I? Okay.
Alpha.
Is there any angle between z2 and z1 as measured along x1?
Theta 2.
Huh?
Theta 2.
No, no, no. See, theta 2 is the angle between x2 and x1. Okay. For alpha I, we need to write the angle between z2 and z1 as measured along x1.
No, there is no
There is
angle.
no, there is no
Twist.
twist. Okay.
Yeah,
And what will be theta 2?
it is theta 1 plus theta 2.
No, no, no. Theta 2 itself. Why? Because
Okay,
theta 2 is the angle between x2 and x1, not x0. Okay. And
okay,
our
okay.
x1 goes like this if I extend my x1.
Yes, yes.
Okay. So angle between x2 and x1 is just theta 2. Okay.
Okay.
And what is di plus 1 in this case?
The displacement.
Again, this is 0.
In zero. Yeah.
Okay. And similarly, if I do for the last link, link 2, okay,
Okay.
you can verify these will be 0, 0, 0. Any problem?
No.
No? Okay.
How it is theta 2?
Okay. So how you measure theta 2 is, the definition of our theta I plus 1 is the angle between xi plus 1 and xi as measured along zi plus 1. Okay. So if I want to measure theta 2, it is the angle between z2 and z1. Okay. As seen along x2.
Okay.
No, 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 no. Wait.
No, no. It
Yeah,
is
I
x2
I
and
placed z2.
x1.
Yeah. Angle between x2
Angle between x2
and
and
x1
x1
as measured along
about,
z.
about the z. Yeah. Okay.
Okay. So this is how we get, because we have defined our x2 here and our x1 has been defined here, and we have said that the angle between them is theta 2. Okay, so
So alpha is like measuring the angle between z I plus 1 and the z I about x
xi.
I xi. Okay.
Yes. Yes.
Okay.
Okay, like if you were there in the last session, we had done an example problem on this SCARA manipulator. Okay,
Okay.
and in this case, we had a link twist. Okay, so like the same problem would be available in many textbooks. You can just take and
Okay.
go and take a look and
Okay.
try to write these parameters.
Okay.
Okay, so now what? Okay, so the whole point of forward dynamics is we want the coordinates. Okay, we want the coordinates of the end effector. Okay, or the tool. Okay, and one way to do that is to write a transformation matrix from 2 to 0. Okay, no, what is the frame attached at the end effector? It is frame 3, right? From 3 to 0, because you see it will be divided like this, t 0 and 1. Okay, and you can get the position of the end effector from this t part, and if you want the orientation also, okay, then you can get from the r part, but most of the time we just want the position of the end effector. Okay, so if you can calculate this t from 3 from frame 3 to frame 0, you can easily get the position of the end effector from this translation part of the transformation matrix. Okay, so now how do you calculate t30 directly? You cannot. That is why we decompose it into this product, okay, with successive frames. I think I have made a mistake here. Okay, this transformation takes you from frame I to I plus 1, but it expresses all the quantities from frame I plus 1 to I. Okay, did you get what I just said? Because this rotation matrix that we were writing there, okay, it was from the new frame to the ground frame always. Okay, and similar is the case between in the transformation matrix from the new frame to the ground frame. Okay, so you have so now you know that it is the transformation between successive frames, so you can just use this result, and you can just plug these numbers for every I plus 1 and I, and you'll get these transformations. You multiply them, you will get this t30. Okay, and then you just extract the translation part from this matrix, and that will be a forward kinematics. Okay, uh, since the session time is over, so I will not do it by hand for now, because then it would take much more time. So are there any questions in what I just explained during this whole session? Hmm. If no, then I would end this lecture.
No doubt, sir.
Okay, then I would end this lecture, and thank you all for attending. You guys can leave.
सर कोई अच्छी बुक हो उसके बताओ ना सर जो
हाँ,
मतलब
मतलब
कंप्लीट
तुम्हें जे क्रेग के बारे में बताया किसी ने?
दिस इज माय फर्स्ट लेक्चर फ्रॉम
क्या?
हियर मेरा पहला लेक्चर है सर यहाँ पे ऑनलाइन
अच्छा, हाँ. So there is a book called Introduction to Robotics by J Craig, CRAIG. Okay, Intro to Robotics. Okay, so this is a very good book for for beginners who are just starting out with robotics. So you should refer this book.
Thank you, sir.
Okay. I am ending the meeting now.